Let's see how we can predict whether a, reaction going to be produce a precipitate. We decide that you we decide that by comparing the Q value, the reaction quotient with its Ksp. Right. So the difference there is the expression for Q and Sp are same, but with the for the Ksp we use only equilibrium concentrations. For the Q we can use any concentration. We normally use the initial concentrations. Right. So, as an example, if we look at the dissociation of the AgCl, the precipitate, that we assume it's slightly soluble and it produces silver chloride and the silver ions and chloride ions. So we write the Q as in silver concentration multiplied by the chloride concentration. This I is for the initial. So if the Q is equal or less than K's p value, no precipitate will form. But if that Q value is greater than or equal to Ksp, the silver chloride will precipitate. That is how we predict predict whether a precipitation formed by comparing the Q and Ks Q and Ksp values. Practice problem 3. Predict whether a precipitate will form when each of the following is added to 650 milliliters of 0.080 molar K2SO4. The first solution to a 250 ml of 0.0040 barium chloride. Right. So you will see, you would assume that, or you would feel that some part of this, the question is missing. Yes. What is the precipitate is forming? Yes, when the sulfate ions from the K2SO4 is mixed with the barium, we get this barium sulfate. For the solution B, now the solution, now the ions from the SO4, sulfate ions from K2SO4 mixed with the silver nitrate, the Ag2SO4. Ag2SO4 precipitate will form. Right. So in this case, the sulfate ions are added by the K2SO4 and barium ions are added by barium chloride in the solution A. In the solution B, the silver ions are added by the silver nitrate solution. So we need to calculate the initial concentrations of the each ion separately. Right. So let's calculate the concentration of the component ions of or the concentrations of the barium and the sulfate ions. Right. For the barium, concentration of the barium 2 plus. It is, how do we calculate the concentration? The moles divided by the total volume. Right. So moles, it is the barium ions are added by the barium chloride. So the concentration of the barium chloride solution is 0.0040 and that is multiplied by the 250 ml. And then it was divided by the total volume. Now two solutions are mixed. So we need to get the total volume 250 milliliters plus 650. So we get the concentration of barium ions, barium 2 plus ions as 0.011. Then we calculate the concentration of sulfate ions. Right, sulfate ions are added by the potassium sulfate. So the concentration of potassium sulfate is 0.0080 and the volume is 650 milliliters. So we get the moles of barium 2 plus ions and divided by the total volume of the combined solution. It is 650 milliliters plus 250 milliliters. So we obtain the concentration of sulfate ions as 0.0058. Now we plug these values to the Q because we don't know whether they are equilibrium concentration. Therefore, we only calculate the Q value, the reaction quotient. So we multiplied those two things and we get this Q value. Now we compare that Q value with the Ksp of the barium sulfate, right? So what does that mean? Yes, now the Q is actually greater than the Ksp value. The Ksp value was 1.1 times 10 to the negative 10, but here it is negative 10 to the 6. Therefore, barium sulfate will precipitate because the Q for this solution is greater than the Ksp of barium sulfate. Solution B. Now we are going to calculate the concentrations of the constituent ions for silver sulfate. So we calculate the concentration of the silver ions. Silver ions are added by silver nitrate. The concentration of the silver nitrate is 0.15 times the volume of that solution is 175 milliliters. We get the moles of that. So we divided that by the total volume of the combined solution and calculate the mole concentration of the silver ions. Then we calculate the concentration of the sulfate ions and we plug those two values into the cube and we obtain the cube as 6.5 times 10 to the negative 6. Then we compare that cube value with the Ksp of the silver sulfate. So look, the cube is now actually smaller than Ksp. Therefore, the silver sulfate will not precipitate. Next, we will talk about the common ion effect. Right. As an example, look at this solution. In a saturated solution of silver chloride, actually the Ksp is given. In here, the equilibrium concentrations of the Ag plus, the silver plus exactly equals to the concentration of the chloride ion because the stoichiometry is equal. So we'll get the equal molar solubility. Right. It is only a saturated solution of silver chloride. Right. What is a saturated solution? Yes, there is a little bit of silver chloride. So it's in equilibrium. Actually Ksp equilibrium. Right. But look now, we are going to calculate the solubility of silver chloride solution containing a solute that has an ion in common with AgCl. As an example, now we're going to add a 0.10 molar solution of silver nitrate to that silver chloride solution. This is silver chloride, silver ions and chloride ion, and this is silver chloride precipitate. And from another source, you will add the 0.10 molar silver nitrate solution. Oh, what is going on? Yes, here is a common ion effect, adding more of the silver ions. In a solution like this, now the concentration of silver ions is not equal to the concentration of chloride ions. So we call this is a common ion effect. Right. But what is the concentration of silver ions now? Yes, that will be equal to 0.10 molar because it is added from a solution. And here the amount contributed from the dissolution of the or dissociation of the silver chloride is relatively it is a negligible amount compared to the concentration of the silver plus added from the silver nitrate. Silver nitrate is actually a solution. So it completely dissociates into its ions, right? It's a salt, so it completely ionize. So we calculate, now we add these things. Now now we are going to calculate the molar solubility, that is S. Now we use that the Ksp expression. We are given the Ksp for the silver chloride as 1.1 time 10 to the negative 10th equals to equilibrium concentrations of the silver plus times the concentration of the chloride ions. Now, the concentration of silver ions will be equal to the concentration of silver ions added from the silver nitrate, which is 0.10 plus S. That the S is the amount contributed from the dissolution of the silver chloride and times the concentration of chloride, which equals to S. So we assume 0.10 plus S is approximately equals to 0.10 because this S is a real it's a negligible amount compared to the 0.10. So we solve for S now, and S is equal to 1.6 times 10 to the negative 9. Look, comparing these two values. Yeah, in the presence of a common ion actually reduces the molar solubility of the solid. Right. What does that mean? Yes, the silver chloride will be less soluble in the presence of a common ion. Practice problem 4. Calculate the molar solubility of silver chloride in a solution that is 6.5 times 10 to the negative molar in silver nitrate. The silver nitrate, okay, the silver chloride and silver nitrate. So, what is the common ion? Yes, the silver is the common ion. So, the content for the silver plus will be added from the silver nitrate and also from the dissociation of silver chloride. Right. So, you write the Ksp, and Ksp equals to the concentration of silver plus multiplied by the concentration of chloride ions. So then we construct this ice table. Right, initial concentration. Yes. Now, this is the initial concentration of the silver plus ions, which was added from the silver nitrate. But the concentration of the initial concentration of chloride ions is 0. Then change. Yes, with the dissolution of that, it will add plus S and plus S. That's the amount that will be added by the dissociation of silver chloride. Right. What is the equilibrium concentration? Yes, equilibrium concentrations for silver ion equals to the 6.5 times 10 to the negative third plus X is, and the equilibrium concentration of chloride is only S. So then we plug these values to the Ksp expression. Ksp is equal to 1.6 times 10 to the negative 10th equals to the concentration of silver, equilibrium concentration of silver ions equals to 6.5 times 10 to the negative third plus S, and the concentration of the chloride ions is only S. So this S is S is a very small value. Therefore, 6.5 times 10 to the negative third plus S is actually uh, equals or approximately equals to 6.5 times 10 to the negative third. Right, now we get the mathematical equation, more simple mathematical equation, which is easier to solve, which is more easy to solve. So now it is multiplied by only S and we calculate the S value. That is 2.5 times 10 to the negative 8. The presence of silver nitrate reduces the solubility of the silver chloride by a factor of 500.